All right, in this video we're going to look at graphing some of the other parent graphs. So if you guys remember, and hopefully you do, we have graphed two parent graphs by hand so far. The first one that we worked with was absolute value. And the second one we looked at was quadratics. So absolute value would be y equals the absolute value of x. A quadratic would be y equals x squared. And when we looked at these two graphs, we went ahead and plugged in some x values. We plugged in -2, -1, 0, 1, and 2. And plugging in those x values gave us some y values. So the absolute value of -2 is 2, -1 is 1, 0, 1, and 2. And this right here helped us to get a picture of what that parent graph looked like. So we'll go over to up to. So we knew that absolute value graphs were these perfect kind of V shapes. And when we did the same thing with the quadratic graphs, we found that they were U-shaped. The reason I'm having you add this to your notes is because we're going to look at the other parent graphs, like what the title says. And this way I figure the notes will be good because you'll have them all in the same place. So let's go ahead and draw this one for our quadratic. So left 2 up 4, left 1 up 1. All right, so when we look at the other graphs, we have the graph that's kind of like a quadratic flipped on its side, and that's a square root graph. And a square root graph is y equals the square root of x. So we're going to do the same thing. We're going to go ahead and make our table, plugging in -2, -1, 0, 1, and 2. And when you plug in -2, the square root of -2 is going to give you an error message. The square root of -1 is also going to give you an error message. If you guys remember when we had square roots of negatives, that's when we put an I in front. We said those were imaginary numbers. Those aren't real. The square root of 0 is just 0 though, so that one works. The square root of 1 is 1. And the square root of 2 is 1.4. So we'll go ahead and draw a little sketch of this one. So we've got the point 0, 0, we've got the point 1, 1, and we've got the point 2, 1.4. So it stops. The graph does not go to -2 or -1. It completely stops there. And so we'll follow it, and it just looks like this. So this will actually be the first graph that we've looked at specifically that has a limited domain. So if you guys recall, domain is the numbers that you could plug in for the x and get an answer. And we have some x values that are outside of the domain. So for this graph, we're actually not going to be able to say a domain of all real numbers or from -infinity to +infinity. We're going to have to limit our answers for that because we've got some numbers we can't plug in. So here is our example problem. We're going to go ahead and use y equals -3 times the square root of x minus 1 plus 5. So first thing, I'm going to draw my chart so that I can graph this. And let me go ahead and zoom in so you can see real well. So I'm going to write these points down again. I have -2 as an x coordinate and error as a y coordinate. You guys will see in a second how I kind of work with that when I make my chart. All right, so the first transformation I can see is that we're reflecting over the x-axis and we're stretching by 3. So that means that I'm going to take the y-coordinate and multiply it by -3. So for the first 2 points, if I multiply an error message by -3, it is still an error message. So I'm going to go ahead and leave those the same. For this one, if I take my y-coordinate and multiply it by -3, I still get 0. If I multiply this y-coordinate by -3, then I get -3. And for this one, I don't want to have too much rounding with this early on in the problem. We should round final answers, but we shouldn't use rounded numbers. So for this one, I'm going to do square root of 2, that's that 1.4, and then I'm going to take that decimal and multiply it by -3. So that gives me -4.2. So 2, -4.2. All right, my next transformation says move them to the right 1. So I'll move to the right 1 and get -1, get 0, get 1, 2, and 3. Move them all to the right 1. Now I have to move them all up 5 for my last transformation. So the error message is going to stay. The error message is going to stay. 0 moved up 5 is 5. -3 moved up 5 is 2. -4.2. If I move up 5 is 0.8. All right, so now I can draw a picture of this. So I have the point 1.5, I have the point 2.2, and I have the point 3.8. Now it can be kind of tricky to see how to connect these points. So think about it this way: at the x value of 0 and the x value of -1, this graph is undefined. That means the graph does not go any further left than that point. So I know that the dots are going to follow it this way. And then if I think about this graph right here, I know that this graph has just been reflected upside down. So I can see that the curve is going to go like this, and it's going to keep going. There's my arrow right there. Okay, so let's go ahead and find some things for this graph. We already talked about the transformations, but let's go ahead and write them down. So I've got reflect over x, stretch 3, right 1, up 5. Now this graph does not have a vertex. A vertex is supposed to be where you switch from decreasing to increasing, decreasing to increasing, or vice versa. So we are not going to have a vertex. However, we are going to have what I like to call a locator point. I'll do LP for short. And the locator point you can find the same way that we did before. So this locator point would be +1, +5. So our locator point is +1, +5. And you'll notice that our locator point in these pictures is where the graph starts. It's this point right here. And you're going to use it for the same things that we did last time. So the vertex often helped us define domain and range and increasing and decreasing intervals. And this locator point is actually going to help us with some of those same things. So we also want, I'm going to go ahead and just make my list here of all the things that we typically look for. So domain and range, increasing, decreasing, max and min, and then x and y intercepts. So for the domain, we have to think about the x values that we were allowed to plug in. We were not allowed to plug in -1. We were not allowed to plug in 0. But we could plug in 1 and 2 and 3, anything bigger than 1. So for your domain, you're going to say I can plug in 1 and anything bigger than that, anything that goes to the right. So that's from 1 to +infinity. The other way you could write that is that you can plug in x values that are greater than or equal to 1. So however you want to write that is totally fine. The range, if we look at this graph, I can see that the lower part of the picture is an arrow that's going down, so that's negative infinity. The highest y value that I can see is right up here, and that has a y value of 5. So negative infinity to 5. Or we're going to say that the y value is 5 at the most and anything less than that. So it's less than or equal to 5. All right. For the increasing and decreasing interval, I'm going to draw a picture like I normally do. So here's my little stick figure, and I can see that as he's walking on this, he's going downhill. That means he's decreasing. And then I need to write down what these x values are. So I have a right arrow, which is an x value of infinity. And here I have that locator point, and that was an x value of 1. So that means the decreasing interval is from 1 to infinity. And again, just like normal, I always use parentheses. For increasing, I'm going to say none. This graph does not go up at all. It's always decreasing. Max and mins, if you guys remember, those are kind of like mountaintops or valleys. So it's a high point and a low point. I'm not seeing any maxes or mins in this picture, so I can see that this is the highest that the graph goes, but it doesn't look like a mountaintop, and that's what makes it so it's not a max. So no maxes, no mins. If I look at the graph, I can see it crosses the x-axis, so I do want to type this in on my calculator. And then I'm going to go ahead and hit graph. And I'm going to do second trace option number 2 like I usually do for my x-intercept. And I'm going to do left bound is going to be right here above the x-axis. And then my right bound is going to be over here below the x-axis. And that gives us an x-intercept of 3.8. And if we look at this graph, you can see that the graph stops before it hits the y-axis because those values were all undefined. They were outside of the domain. So for the y, don't put a parenthesis, we're not writing a point. The y-intercept is none. There aren't any. All right. I don't want to make the video too long, so we're going to stop there and we'll do the other 2 types of parent graphs in class. We've got 2 more. We're going to look at cubic graphs and cube root graphs. So 2 more parent graphs to look at.